So this is a continuation of lecture 3 on model formulation for LP, or linear programming. And the next example that we are going to discuss is the urban development planning example. And in this problem, we have a city that is trying to use their budget, or the budget of the city to plan for new homes for the citizens. And the city is faced with a severe budget shortage. And the city council votes to improve the tax base by condemning a inner city housing area and replacing it with a modern development. This project has two phases. The first phase is to demolish substandard houses to provide land for the new development. And the second phase is to build the new development. So in this problem, we're going to have to account for the cost of demolishing the current houses that are in the land. And then we also have to account for the cost of building the new homes. And here we have some extra information. As many as 300 substandard houses can be demolished. Each house occupies a 0.25 acre lot, and the cost of demolishing a condemned house is $2,000. Lot sizes for new single, double, triple, and quadruple family home units are 0.18, 0.28, 0.4, and 0.5 acre. Streets, open space, and utility accounts for 15% of the available space. So we have to account, not only for the homes, but also we have to separate some space for the streets, the open spaces, and so on. In the new development, the triple and quadruple units accounts for at least 25% of the total. Single units must be at least 20% of all units, and double units must be at least 10%. So those are constraints for our problem. The tax levied per unit for single, double, triple, and quadruple units is $1,000, $1,900, $2,700, and $3,400, respectively. So that's kind of a income that you will get. The construction cost per unit for single, double, triple, and quadruple family homes is $50,000, $70,000, $130,000, and $160,000. And financing through a local bank is limited to 15 million. So the question we are trying to answer is how many units of each type should be constructed to maximize our tax collection. Okay, so as we mentioned, we have this space that is occupied by what they call substandard houses, about 300, and each house occupies 0.25 acres. So as we demolish, we are gaining space. And then the question is, if we need to build, are we going to build single, double, triple, quadruple new homes? And also how many of each? And we have a cost, we have tax information, and we have also a constraint in terms of the financing that is available. So the question again is how many units of each type should be constructed to maximize our tax collection. So questions to be answered: how many units of each type, as I mentioned already, should be constructed or demolished to maximize the tax collection? So we're going to have an index I representing the type of home. And our decision variable is xi, which is equal to the number of units of type of home I. So this includes the 4 different levels, or the 4 different layouts for the new homes. The variables of the model are the number of units to be constructed of each type of housing, And in addition to that, we're going to have an index representing the number of houses that must be demolished to make room for the new development. So we have the following decision variables. X1 is represented single family homes, X2 is represented double family homes, X3 triple family homes, and X4 the quadruple family homes, and then X5 is representing the old homes that are going to be demolished. So we can demolish up to 300, but we have to find that balance. Our model is going to help us find the balance in terms of how many to be demolished up to 300 and how many are going to be built and which type. So our objective function is to maximize the total tax collection from all 4 types of homes. So the objective function is going to maximize the tax collection for each type of home. So as we mentioned, it's 1,000 for single, 1,900 for double, and so on. So this is going to be our income, if you want to see it that way. So we want to maximize that. And then we have some constraints in terms of the space. So the first constraint of the problem deals with the land availability. So we know that if we are going to build new homes, we have to have some space available. So the acreage used for new homes construction must be less than or equal to the net available space. We have information about the space needed to build new homes, and that is what is represented here. So this is information that we have for single, double, triple, and quadruple. So this is the space that we need. So we know that the summation, depending on how many of each we're going to be building, the summation of it cannot exceed the space available. But in order to determine the available space, each demolished home occupies 0.25 acre, thus netting 0.25 x5 acres per home that is demolished. So we have that information. We have the space that is needed per unit, new homes. We have the space that is going to be available as we demolish X5 or we increase X5. And now we have to account also for the 15% open space street, and for the open street is the open space and so on. So the net acreage available is going to be 0.25 times X5, which is the number of units that we're going to demolish. But the space available, the actual space available for us to build new homes is going to be less than that, because we have to save 15% for the other, for the utilities, the open space, and so on. So we have to multiply that amount by 0.85. So that multiplication gives us this much. So instead of 0.25 acreage available per unit, we're going to have 0.2125, because 15% of that is going to open spaces and utilities. So the resulting constraint is as follows. The summation of the new development in terms of space needed has to be less than or equal to the space that is going to be available. This space is going to be is going to depend on how many units we are going to demolish, and the new development is going to be based on the number of units that are single, double, triple, and quadruple. So putting all this together, we can move this to the left-hand side, and this we have this equation. 0.18 times x1 plus 0.28 x2 plus 0.4 x3 plus 0.5 x4 minus 0.2125 x5 has to be less than or equal to 0. The number of demolished homes cannot exceed 300. So we stated that at the beginning. So what that means is that X5 has to be bounded less than or equal to 300. And then we have the constraints limiting the number of units of each home type. So as mentioned, for single units, we want single units to be at least 20% of all units. Double units has to be at least 10% of all units, and triple and quadruple has to be at least 25% of all units. So for us to determine or to write that constraint, we have to make sure that we provide that lower bound for X1. So 20% of the summation of all units, or all new units, have to be for X1. 10% of the summation of all units has to be for X2. And then 25% of all units has to be for X3 plus X4. Two additional constraints keep the demolition construction costs within the allowable budget. So we have this limitation in terms of funding. So construction and demolition costs has to be less than or equal to the available budget. So expressing all costs in thousands dollars. So this was 15 million. So now we are making those in terms of $1,000. So this is representing $15,000, which is going to be equal to 15 million. So the summation of the construction plus the demolition cost for the units that we are going to recommend has to be less than or equal to that 15,000 of 1,000 or $15 million. So this is the objective function. We want to maximize the tax collection, and we know that that's the maximization objective function, and then that's going to be subject to these 6 constraints. And don't forget to also include the bounds. So we want our decision variables to be positive. So all decision variables have to be greater or equal to 0. The next problem is called the project selection problem. And in this one, we are going to be using some economic analysis, net present value concepts. So in this problem, we have the Star Oil Company is considering 5 different investment opportunities. The cash outflows and net present values in millions are given in the table. So you can see the investment. So these are the 5 options of investment. 1, 2, 3, 4, 5. And these are the cash outflows at time 0 and also at time 1. And we have the net present value for each one of the investments. So Star Oil has 40 million available for investment now at time 0. And it estimates that 1 year from now, time 1, 20 million will be available for investment. So right now we have 40, and then a year from now we will have 20. Star Oil may purchase any fraction of each investment. In this case, the cash outflow and net present value are adjusted accordingly. So for example, if the company purchases 1/5 of investment 3, then a cash outflow of 1/5 of 5 equal to 1 million will be required at time 1. The 1/5 share of investment 3 will yield a net present value of 3.2 million. Star Oil wants to maximize the net present value that can be obtained by investing. So we want to formulate an LP that will help achieve that goal. Assume that any funds left over are at time 0 cannot be used at time 1. So what are the questions to be answered? What fraction of each investment to purchase? So we're going to have an index representing the type of investment for the problem. And the decision variable xi is going to represent the fraction of investment I to purchase by the company. As the problem stated, we want to maximize the net present value earned from investments. So our objective function is the summation. We want to maximize the summation of all net present values per investment. So 13x1 plus 16x2 plus 16x3 plus 14x4 plus 39x5. So going back to the table, we're gonna formulate our constraints. So start oil constraints may be expressed as follows. Per constraint means that we cannot invest more than 40 million at time zero. And also we have constraint 2 that says that start cannot invest more than 20 million at time 1. And the last constraint is that start cannot purchase more than 100% of an investment. So the first constraint is going to use the cash outflow for time zero for each one of the investment. So we know that start cannot invest more than 40 million at time zero. So the summation of the cash outflow for year 1 has to be less than or equal to 40. So now you have to decide which investment you're going to pursue. You remember this could be fractional values, and the net present values will also be adjusted based on that fractional value if you end up purchasing not the whole thing, but a fractional amount of the investment. Start cannot invest more than 20 million at time 1. So same thing now, we are looking at time 1. So that those investments cannot exceed the 20 million. And then start cannot purchase more than 100% of an investment, which means that we can, each decision variable has to be less than or equal to 1. So fractional investments are allowed, but you cannot exceed 1 in terms of purchasing an investment. So this is our formulation. We want to maximize, again, the net present value of the earned from the investments. So that is the maximization of Z, which equals 13x1 plus 16x2 plus 16x3 plus 14x4 plus 39x5. And then we have the constraints that we just discussed. So the first one is looking at the amount that you are going to invest at time 0. And then this is at time 1. And each investment has to be less than or equal to 1. So we have 5 options. All of them has to be less than or equal to 1. And that's your formulation for the investment or project selection problem. Okay, the last example or the last problem that we are going to discuss in this lecture is the blending and refining problem. And I chose this problem because I know some students will have interest in going to work for an oil company. So this is our typical problems that you will find there and that can be solved using linear programming and operational research. This problem is longer than the previous problems that we discussed, but it's very interesting. This oil company has a capacity of 1.5 million barrels of crude oil per day. The final product from the refinery includes 3 types of unleaded gasoline with different octane numbers. So we have 3 different gasolines that can be produced with different numbers of octane. The refining process encompasses 3 stages: a distillation tower that produces feedstock with this value ON82 at a rate of 0.2 barrels per barrel of crude oil. A cracker unit that produces gasoline stock ON equals 98 by using a portion of the feedstock produced from the distillation tower at a rate of 0.5 barrels per barrel of feedstock. And then we have a blender unit that blends the gasoline stock from the cracker unit and the feedstock from the distillation tower. The company estimates the net profit per barrel of these three types of gasoline to be $6.70, $7.20, and $8.10. And the input capacity of the cracker unit is 200,000 barrels of feedstock per day. The demand limits for regular, premium, and super gasoline are 50,000, 30,000, and 400,000 barrels per day. So the question is, can we develop a model for determining the optimal production schedule for the refinery? So we have all the information we need. You maybe need to have a, let's see if I have that figure. Maybe I can draw a picture of the process here. So we had the distillation, then we have the cracker, and then we have the blender. Okay, so the crude oil comes here. Then from here, we can send some of the distillation product to the cracker, and then some of the product will go to the blender. And then from the cracker to the blender, we have some product. So there's a 5-to-1 rate. So 5 barrels of crude will produce 1 product of ON equals 82. So this is ON 82. And some of it will go to the cracker, some of it will go to the blender. And then in the cracker, we have a ratio of 2-to-1. 2 barrels of crude or feedstock will produce 1 of ON 98. And then from the blender, we have a 1-1 relation. And then you have 3 products coming out. You have ON equals 87, ON equals 89, and ON equals 92. So we want to develop a model to determine the optimal production schedule for the refinery. So what are the questions to be answered? How many barrels a day to produce certain type of final product? So I is going to be used to determine the barrels a day of input stream I, and then J is the blend of the final product J. So I, J, and different blend. J is for the output, I is for the input. So Xij is barrels a day of input stream I used to blend final product J. So this is the first time I believe that we have 2 indexes representing a decision variable. So it works the same way. Now we have 2 indexes. So let's say if I equals 1 and J equals 1, then we are using input stream, let's say ON equals 82 will represent 1, And then this is for the final product. Let's say that ON equals 87. So what this is saying is how many barrels of this feedstock 82 you're using to produce gasoline with ON equals 87. So this will be X11 in this case. X11 will be how many barrels a day of input stream I is used to blend. So barrels a day of input stream 82 is used to blend final product 87. So here are the definitions. So using this definition, we can define the following. The variables can be defined in terms of two input streams to blender, the feedstock and the cracker gasoline, and the three final products. So that feedstock is this piece right here. This is your feedstock. And this is what's coming from the cracker. So those are your I equals 1 and I equals 2. And then this is J equals 1, this is J equals 2, and this is J equals 3. So using this definition, we have the daily production of regular gasoline is X11 plus X21. So basically, you are combining the two ways that you can produce regular gasoline. So you can produce it using the feedstock directly, or you can produce it using this cracker. So those two inputs can be used to produce this. So that's what this is representing, this first piece here. And then for the other two is the same, daily production of premium gasoline. Then the only thing that is changing now is the J value. So for the first one, it was 1. For the second one, J is 2. And for the third one, J is equal to 3. So we want to maximize the total profit. So the profit is going to be based on how many barrels we sell for per product, regular, premium, and so on. So we can multiply the definitions by the profit, $6, $7.20, and $8.10. And then in terms of the constraints, and here's the figure, a better representation of the figure at the top. The constraints we have the following. We have the daily output of the blender unit has to be equal to the daily production of regular gas plus the daily production of premium gas plus the daily production of super gas. So that's going to be equal to this expression right here. So we have the daily feedstock to blender. We have the daily cracker unit feed to blender. And we have the daily feedstock to the cracker. And the daily crude oil use in the refinery. So knowing all these expressions, we can formulate the following constraints. So the daily crude oil supply does not exceed this 1.5 million. So the summation of this and this has to be less than or equal to that. And then the cracker unit capacity does not exceed this much. So that expression that we use to define the input to the cracker unit is less than this much. And then the daily demand for regular does not exceed this. So we want to make sure that we don't produce more than what's needed. Daily demand for premium. same thing. We don't want to produce more than what is needed. And same thing for super. We don't want to produce more of what's needed. In terms of the octane number of a gasoline product is the weighted average of the octane numbers of the input stream used in the blending process and can be computed as follows. So the average ON of regular gasoline is going to be equal to the feedstock ON plus times the feedstock barrels a day plus the cracker unit ON times the cracker unit barrels a day. All that divided by the total barrels a day of regular gasoline. So for octane number for premium is at least 87. We can use that information or that equation to compute that. So it's going to be 82 times X11 plus 98, which are the octane for cracker and the barrel. I'm sorry, for the feedstock and the cracker. So we can find that weighted average multiplying X11 by 82 and X21 by 98 and divide everything by the total gasoline produced, and that has to be greater than 87. If we want to make this a linear equation, then we can solve for, we can move this to this side, and then we have this linear equation. And same thing, we do the weighted average for ON equals 89 and the ON equals 92. So finally, we have the blending and refining LP formulation. So as I mentioned at the beginning of this example, this is a little bit more challenging in terms of all the details, and also in terms of using 2 indexes instead of 1, I and J. But this is a final formulation. So this problem has 1, 2, 3, 4, 5, 6, 7, 8 constraints. The bounds has to be positive those decision variables. And this is a final formulation. So this completes this lecture on formulating linear programming models. As I mentioned in the first video for this lecture, model formulation for linear programming requires a lot of practice. So the more experience you gain, the better you'll become in terms of formulating these problems. But it's important that you create your own library. So I gave you a good list of problems in this lecture. You can keep those and have them in the future. You might face problems that are similar to those that we discussed in this lecture, and you can refer to those models and use the format maybe to formulate other problems in the future. And that concludes this lecture.